can also partition the users, but partitioning users will give us some sampling error. So we may use the split privacy budget approach. Right. So the question is, what about the local setting? In the local setting, if we assume there are many users and we assume the sample invariance is small, we can measure the variance of either approach. And we found that if we split privacy budget, we will get this variance. And if we partition the users into groups and ask each group a separate answer, a separate question, we will get this kind of variance. And if we calculate no matter algebraically or numerically, we can see that partitioning users will give us a better result. And so this calculation can also be generalized into any number of Q questions instead of only 2 questions. Yeah, so another maybe somewhat important factor is that once we get the result, so for example, the left column is the true answer, the middle column is the expected answer, and the right column is the amount of noise in their absolute values. So we can see the amount of noise is pretty stable, but if there is some category that has a true answer that is already pretty high, the estimation will not be dominated by the noise. But on the other hand, if for example, the final carry tree, the original count is 0, it may, with a very high probability, the estimated count is dominated by the noise. So there is some threshold, a significant threshold that, so for example here that is around 15, I would see that if the estimated count is less than 15, maybe we want to just discard the estimation and assign their estimated probability to 0. All right, so because it's totally overwhelmed by the noise. So the summary so far is that we have covered frequency oracle, which is built on randomized response, and we also cover some thoughts on how to use frequency oracle. And so here is the table that summarized what we have currently. So for the categorical setting, if the value is one value, we can use frequency oracle. But if the user has multiple values, we may want to split privacy budget. Split the users instead of splitting privacy budget. So now, if we move on to from categorical data to numerical data, one also maybe thinking about how can we handle the numerical setting. So here is the what we call numerical mean oracle, which just handle the numerical setting. So similarly, each user will also has a encoding function and a perturbing function, and we assume now that the domain is from -1 to 1. So that is my preference, but we can assume the domain from 0 to 1 and whatever. And then the user will send the report to the server similarly. And the goal of the server now becomes to estimate the mean. All right, so the user will only have one information, that is the mean of the values of the users. Yeah, so there are, I would say, basically 2 papers talking about this. Their mechanisms are, to me, equivalent, but they assume different ranges. But let's see. So before we come into their algorithms, one can also use other mechanisms, right? So if we are familiar with the centralized DP, we can add the Laplace or Gaussian noise. And if we are familiar with the categorical setting of LDP, we can also use the frequency oracle. That is, we bucketize the domain into several buckets and do the frequency estimation of each bucket. That actually has some extra information of the frequency, but the problem with it is that we cannot have the optimal bucketization structure. So, for example, if all the values are just above the are just in the lower range of the bucket, then that the result may be inaccurate. So the method of the two papers I mentioned earlier just used this very simple idea that the encoding function will do the probabilistic assignment, which I think Devesh has also covered in this morning. I don't know if you still remember. Yeah, so specifically, if we assume V is from -1 to 1, and it is continuous, and the encoding function will perturb or just assign one value that is -1 or 1. So the assignment probability are these two. So they sum up to 1, and as we can see, the more close the value to 1, the higher this probability, right? So this step actually will ensure that the encoding is unbiased. And after getting this bit, we actually transform the numerical setting to the categorical setting, and we can just apply the frequency oracle to get the result. Yeah, so in real world, there are some complicated settings where first that the range may not fall just into -1 to 1, and in that setting we can just convert and then convert back the result. And another setting is that each user may not only have one numerical value, but instead a vector of numerical value. So in that setting, one better off also use the split users into groups approach, and that will give a better accuracy. So summary so far, we start from randomized response and cover the frequency oracles, which is used to handle the setting where the domain is categorical and each user has one value. And we also handle the setting where each user's value is not one value, but a vector of values. And the goal is to understand the distribution of each single dimension. And for the numerical value, we use a mean oracle which is a combination of a probabilistic assignment and a randomized response to handle this setting where each user only have one value. And for the vector thing, we also recommend just split users into groups. Okay, so I think I'm done for the LDP algorithms, but let's focus on some applications now. So the final part of my talk is heavy hitter identification and frequent item set mining, the two problems, which are slightly different from the settings we assumed earlier, which is quite simple. So first of all is heavy hitter identification. So the problem is simple. I think Apple or Google is also interested in this problem, and Devesh has also given us the idea. So that is, if the domain is very large, so we assume the D is quite large, because otherwise we can just apply the frequency oracle and get the result, which is quite straightforward. So, and we also assume that each user has a single value which is represented in bit. So if we think of each user has like 128 bits, then the domain will be very big. Using frequency oracle directly will be infeasible. So before attacking this problem, we may want to think about a simpler problem of finding only one frequent item heavy hitter in a very large domain. So the idea is still to partition the users into groups. As you can see, this is an example that has 4 segments. So 4 bits might be too simple, but if we think of 4 characters, which might be 32 bits, right? So each user will report one portion of its string. And the server will query the frequency oracle for each one of them and concatenate the result to get one heavy hitter. And that's a pretty simple approach to a pretty simple problem. So if the goal is to, instead of finding only one heavy hitter, now is finding K, the most frequent heavy hitters. Using this similar method cannot scale, because after getting the frequent patterns in each of the 4 locations, the candidate pool will be composed of the Cartesian product of all the 4 sets of frequent patterns, which might be big if the number of bits are very big. Yeah, so because we need to do a parity product, it cannot scale very well. Yeah, so there are proposals for handling this problem, which so the first 2 are kind of already beaten by the 3rd class, so I will not go into details. Maybe go very quickly. So the first is called segment pair. It allows each user to report 2 segments, right? And then the server will find the frequent pattern for each location and for each pair, and then build a k-parted graph and query for the cliques, which corresponds to the heavy hitters. And another approach is to use hash function. The idea is to use hash function to isolate different heavy hitters, so that we come back to our very first very simple question of only identifying one heavy hitter. Yeah, so but the communication cost is still high. Yeah, so I would say the state-of-the-art class of algorithms are called prefix extending methods. So the idea is also quite simple. So for example, in this very simple example, we have 4 groups, and we assume they all have the same value, which are 8 characters. So the first group of users will call the perturbation function of we assume using OLH. That perturb the first 2 characters, and then report to the server who queries all the first 2 characters and identify that the most frequent first 2 characters are DE. The second group will then report their first 4 characters and the server can query not all the all the possible 4 characters, but only condition on that there are 2 characters are already identified, and all the possible second 2 characters, and then maybe find that the first 4 are dead. And similarly, the third will just do for the first 3 characters, and the server can also get the first 3 characters, and finally we can build the frequency, the frequent heavy hitter for the whole domain, which is, I guess the key idea in this is kind of also straightforward. So as we can see, there are several proposals for this style, which has very similar structure and very similar ideas. And so the difference is that the first proposal proposed to partition users into M groups, where M is the number of bits, so that we kind of improve on bit by bit. Okay, so the second proposal is to partition the users into as few groups as possible, so that each group will report as many additional bits as possible. And the third pre-try method, which Graham will talk about more detail later, is first of all, it's interactive. That means it will go back and forth, send messages to the users. And also, it's kind of handle a slightly different approach, slightly different setting. So one research question is that how can we determine the additional bits each user contribute? So the intuition is that each user, if we allow more bits, we end up having less groups because the total number of bits are fixed. And as a result, there will be more users in one group, so that the accuracy for one group will be higher, right? Because the more users I have, the more accurate the result will be. But on the other hand, another design principle will be I want to let each user report as less bits or as few bits as possible. Then, because there are fewer bits, the number of candidates for each query will be fewer, right? Instead of enumerating all the 2 to the 8, we now enumerate all the 2 to the 4, which will give us less likely that an infrequent item becomes frequent after the frequency oracle query. So our approach is to analyze the expected utility score, which turns out to be an optimization problem. Yeah, so this is just how the optimization problem looks like. I will not go into detail, but the findings are that, first of all, ideally, but obviously infeasibly, the optimal approach would let all the users report the full string. And the server just probe the frequency oracle for all the possibilities and get the k-frequent heavy hitters. So that it turns out the computation cost of the server becomes a constraint here. And the proposal is that under the computational cost constraint, we want to let each user contribute as many bits as possible. Yeah, so that is the lesson learned from this problem. Yeah, so finally is the frequent item set mining problem, which handles a slightly different setting, where we have also several users. Each user will have a set of items at their private values. And each user still report to the server using LDP. And the goal is to find the frequent, first of all, the frequent singletons, and then the frequent item sets. So for example, in this example, we have 5 users. The top 3 singletons will be E, A, and B. And top 3 item set will be E, because E as a singleton is also an item set, right? Will be E, A, and AE. So a strawman method for this problem would be to encode the item set as a value and use the heavy hitter solutions we just go over to handle this problem. But the disadvantage of this approach is, first, it cannot scale to very large amount of possible items. So if we have like 10,000 possible items, this is totally infeasible. And secondly, if even if one item appears frequently in some of the users, the encoding thing may not be identified, right? The encoding item set may not be identified. And so there are basically 2 proposals, and let's take a close look at the 2. Yeah, so both of the methods assume sample and pad and sample based frequency oracle. That is, each user's item set is has different lengths, but we first pad them into a fixed length. So note here the final user has 6, but one can truncate either one. That is conceptually equivalent. And then each user can just randomly sample one. So note that the padded item might be dummy, so the sample item may also be dummy. And finally, the sample item will be reported by some of the frequency oracle. And the server will aggregate the result and then multiply by L at the final result. So this is basically the pad and sample-based frequency oracle. So the idea of it is that when many users have this item, the probability that it is captured in this after sample phase is high, so that we finally can capture this item. Yeah, so the first proposal is called LDP Minor. It has 2 phases. The first one is to identify the candidate. So they pad the size of each bit to L, which is the 90th percentile of the size distribution. Right? So that at least at most 10% of the users will have to truncate their item after padding. And then each user will randomly select one report. And finally, the 2K potential frequent items are returned to the users in the second phase who will contribute to estimate the frequency. So in the second phase, each user will first intersect the private value with the 2K items, so that each user will have at most 2K items, right? Because there is an intersection. And after that, each user pad to 2K and randomly select one and then report. Yeah, so we took a closer look at the approach and found that this approach can only find the frequent items and leave the frequent item set as an open problem in their paper. And secondly, it does not choose optimal solution in some settings. So first of all, the value L affects the error in the 2 ways. And secondly, the sampling also has a privacy amplification effect. So those 2 are our observations, and we will take a look at that. So the first observation is that there are basically 2 phases that will add noise. One is this reporting or perturbing thing of the frequency oracle. Another is that because the result is multiplied by L, the variance is multiplied by the L squared, which is quite bad if we use a very large L. Yeah, so another source of error is that if a user has many items, the truncation may make this biased. So there are basically two errors that L will affect. So it may be a trade-off how to choose L, right? So the larger L, the larger the variance, but the smaller L, the larger the underestimation. But it turns out that depends on the goal of our setting. So as we can see, we have two options. First is to set L to be quite large. Another is to set L to be quite small. So the bad thing about the approach to the left is that some users may just report dummy, making the overall signal very weak. And the observation of the right approach is that even if each user underestimates its item sets, the relative ranking of the items are pretty stable if we have many users and a lot of items. So as a result, when the goal is to identify a set of candidates in this problem, we propose to use a smaller L. So another observation is this privacy amplification effect under sampling. So we already know that in the traditional LDP or in the simplest setting, we have this bound. But after a sample is involved, this thing might be different. For example, if we think a randomized response is used, the probability will be the probability of perturbation multiplied the probability of the sampling. So as a result, if we examine this probability carefully, we will see that if we use randomized response and we want to use epsilon as the privacy budget, the epsilon prime that is used by the randomized response can be actually larger than epsilon, which is some benefit by the sampling step. Yeah, so in our algorithm, we choose to adaptively choose better frequency oracle based on variance. But here, the randomized response will have a strictly lower variance. So that may change the guideline. So as a result, there is this swim method, which has three phases. The first phase is to identify identify the candidates, but only let L equal to 1 compared to a very large L. And the second phase is also the estimating the the second phase will be to estimate the length distribution. Instead of using 2K in the surface, we will use L, which is 90th percentile in the surface. Yeah, so this is a basic diagram of the approach. Note that the top half are for the frequent item mining, and the bottom half is for the item set mining, which will have more detail in the paper, but I will not cover it here in the tutorial. Yeah, so some empirical results that show that some utility will be multiplied by 3 times if we take this approach. Yeah, so with that, I finish my part, and I would like to take any questions. If not, I will hand over to Graham.
One hour. That's so much time. Great. Okay, can you make it appear? That would be useful. Yeah. Beautiful. Okay, so let's wake up from our post-lunch slumber and recap. Where are we? So we're looking at this model of local differential privacy. We've motivated it through the real-world deployments, and Tianhao has taken us through everything from the initial definition through the basic mechanisms up to applications like finding frequent items and frequent item sets distributed over your population. So this next large chunk, we're going to be looking at applications, other applications that have been studied in this LDP model. When we started looking at this tutorial, I thought this is great. This is a nice sort of self-contained, well-defined area. And then the more we looked at the literature, the more we found was out there that people have been looking at just over the last 2 or 3 years. So what I'm going to do here is introduce each of these applications and not get too deep into the technicalities. And that's partly because you don't need to get too deep into technicalities. A lot of the work in these papers is in defining and modeling the problem in such a way that you can then invoke one of the techniques we've seen already, and that's the bit that kind of gives you, at its core, the local differential privacy and solves the problem in question. So I'm going to run through each of these applications, and we'll see how we get on in terms of time. So I'm going to start with one of the sort of an application that's sort of at this boundary between directly picking up some of the existing techniques. In the area of text, right? So some of the basic applications we've seen of LDP have been in text, right? Apple want to identify what are the new words people are typing on their phones so that they can add them to their autocorrect dictionaries. Or more generally want to look at other aspects of language use over text, particularly from mobile users. So this is interesting because what we looked at before was data that was coming from we assumed the data was coming from a structured domain. We started off looking at a binary domain, then we said, what if it's some fixed D, and then heavy hitters over a slightly larger domain. Now potentially we're thinking about possibly very large domains, URLs that are drawn on alphabets, but potentially very long. So I'm going to try and briefly say something about a few papers here. I'm going to pick up on n-grams because this is closest to where we just left off with frequent items, heavy hitters, and frequent item sets. So this is exactly in this sort of data collection from mobile users setting where you're thinking about how do I learn what are the new popular terms that people are using, the words people have made up or the slang that I can add to my dictionary. So it's simplified by saying assume everyone's just got one new term. Not really discussed how you generalize that, but it's fairly easy to generalize that to multiple new terms. So as soon as you do that, you realize, well, it's another heavy hitters kind of problem. It's just a heavy hitters over words. And indeed, the way you model it looks kind of familiar compared to the way that Tianhao was saying how you might search for heavy hitters over a large domain. I'm going to think of this really as sort of searching within a trie. Right? The words that I'm interested in, with a sort of a start word and an end word character over this binary alphabet are just sequences. I can conceptually think of a trie over these sequences where each internal node has a count that tells me how many occurrences there are. And what I want to do is explore this trie, sort of top down, to sort of find the heavy nodes within there. Right? And we have this prefix property that says if there's a heavy node internally, then all its ancestors must be heavy. So it leads to a fairly immediate search algorithm, start at the top, descend down. The question is just, well, how do I make sure that this meets local differential privacy? So this